Good day. My name is Neil Mattson. I'm a professor and greenhouse extension specialist at Cornell University in New York. And I'm going to talk about water quality for both soil and soilless production systems. And this could be relevant for both vegetable crops as well as floriculture or nursery crops as well. So should be kind of a fun discussion. And thank you for the invitation and having me today, Talia. I was super excited that I get to speak to Nova Scotia growers because one of my favorite folk songs is by the Irish Rovers, and it's called Farewell to Nova Scotia. And I tend to have that song stuck in my head or for about a week anytime I think of Nova Scotia. So yay. And then on the left side is just a view outside of my office. I'm on the sixth floor. I don't have a window in my office, but if I walk down the hallway, this is my view of Cornell's campus and our surrounding hillsides today. So it's a beautiful day in New York. Okay, we're going to dive into water quality. Um, the question is always like, okay, I have this water source on my farm, on my operation. Is my water good for growing plants? What are the issues that can come up with the type of water that I have? And so there's a bunch of different characteristics, and I'll go into some of the more common ones. And how do we then take into account what our water quality is and then make adjustments in our operation in either, I'll talk about the soil-based systems as well as soilless systems. So understanding your water quality is going to start with a laboratory test. So finding an agricultural operation or a lab service that's used to working with agricultural operations so that they're testing the right things. I'll show some examples of testing labs that we have in the US, but I bet our friends at Perennia can really help you find more local testing sources. So these will be the things that we're looking for, and I'll share a second screen with some more things. So what makes good quality water is usually having a pH of 4.5 to 7. We can make adjustments from there because ultimately the water will affect the pH of our soil or soilless mix. As I'll talk about, it's really the alkalinity of the water that has a more long-lasting effect on the root zone pH. And so the alkalinity is the carbonates and bicarbonates that are in our water. And if you're used to working in soil production systems, when we need to raise the pH of the soil, we add limestone, and it's the carbonates and bicarbonates in limestone that are raising the pH. So I always like to think of alkalinity as liquid limestone, so to speak. It's the higher your water is in alkalinity, and the more you add, the more your pH is going to go up over time. So it tends to be that we think kind of moderate alkalinity of water is ideal because that gives us some buffering. So we don't have, if alkalinity is too low, we can have poor pH buffering and pH can crash or pH can go down too quickly. So for less than about 40 parts per million calcium carbonate, we have those issues. Then 40 to 100 parts per million we kind of consider ideal. And then starting to get more than about 100 parts per million, then the more water we add, the more the pH is going to go up over time. And so in that case, we really need to think through, and I'll give more details on either acidifying our water source to neutralize some of that alkalinity, or to make amendments to our soil, like adding elemental sulfur to our soil, or choosing a more acidic fertilizer to keep the pH in check. Then another overall measure of water quality is the electrical conductivity. That's a measure of all of the salts that are dissolved in water. That measurement doesn't differentiate between what's a fertilizer salt and what's a non-fertilizer salt, like sodium and chloride. But in general, the saltier our water is, it's going to make it harder to grow plants over time because salt can build up in our root zone. So our typical guideline is if you're growing young plants, they're more sensitive to high salts. Ideally, our water source is going to have an EC less than 0.75. And then if we're growing general plants or mature plants, we can usually get away with saltier water, so the EC can be about 1.5 decisiemens per meter or lower. And then the higher the EC is, the more we would have to think about our own management practices to mitigate salt accumulation in the root zone. So we would need to do more leaching or have a higher leaching fraction if we're growing container plants, for example, to push out that salt. If you're in soils, if we're outdoors in soils, we kind of depend on Mother Nature to rinse away or flush away some of those salts if we're outdoors. But if we're under protection, like in a high tunnel, then that becomes a problem. Like salts will build up in the soil and it can be harder to flush them away. So we'll get a little bit more into that as we progress. And that one I don't have great answers, but some like starting points. So then we take a look at some of the individual components, some of the individual elements that can be in our water. So beyond EC, for example, we'd want to know what is the sodium and chloride concentration. And if those are higher than about 70 parts per million, we can sometimes see damage to roots and foliage. Nitrogen is a plant essential nutrient. And so if the one thing that we're worried about is in terms of potability or drinking of water, um, is high nitrogen will render drinking water unsafe. But for agricultural crops, we can take advantage of that extra nitrogen. The one thing that having a nitrogen um, amount of more than 10 parts per million suggests to me is that maybe the water source is a surface pond or a shallow well or something like that. And so there's some source of nitrogen, like agricultural runoff into our shallow well or into our pond that's giving us that nitrogen. So that would then cause us to think about, okay, what are maybe water quality issues from that, which also could include like spreading root-borne diseases or something from a surface pond. Phosphorus is usually less than 5 parts per million, unless, again, we have agricultural runoff. Potassium is a plant essential nutrient. There's not particular concerns with more than 20 parts per million. Potassium, we can just take into account how much potassium we have and decrease that level in the fertilizer. And then another set of parameters to look at. So I bolded a few that I want to touch on. So calcium, if it's more than 150 parts per million, we would definitely want to take that into account in terms of decreasing the amount of calcium in our fertilizer. Similar thing with magnesium. Also, we often look at the calcium to magnesium ratio, and a lot of our fertilizer recipes, we give plants about 3 parts calcium to 1 part magnesium. So if magnesium happened to be very high and calcium happened to be very low, that would indicate to me that I need to add more calcium to make sure that our plants have sufficient uptake. Iron is sometimes an issue in that iron concentrations more than about 2 parts per million can start to become toxic for sensitive crops. We can also get iron staining. So I grew up on a farm with a well, and we had lots of iron in our household well. And so we got iron staining of white clothes, for example. So I had to use iron out when I washed my white uniforms to work at the hospital in town. So similarly, our plant leaves, if we're doing overhead watering, they can actually get iron stained sometimes. And then maybe the larger issue in terms of water quality with iron is if we have high iron concentration, that's a food source for iron feeding bacteria. And so we can get kind of like sludge or biofilm from the bacteria that feed on high concentrations of iron. And maybe the other one I'll just mention is if you have a source of water that's from a town, a municipality, they might be adding fluoride to it. And then fluoride can be, so they add fluoride sometimes. We do this in the US to improve our health of our teeth. So we have less cavities. However, at more than about 1 parts per million, we can start to get fluoride toxicity for sensitive crops. Those tend to be ornamental crops that are like foliage crops, like monocots, for example. And the tips of the leaves are where fluoride builds up on those older leaves, and we get browning or scorching of the leaves. So As I mentioned, you will definitely want to get, if you haven't done this in the last few years, get your water source tested by an agricultural water testing lab. In the US, here's some of the companies that I refer folks to, and I'm sure our friends at Perennia can tell you where to go in Nova Scotia or surrounding provinces to get your water tested. When you have those results, this is an example of what a water analysis for greenhouse crops looks like from a commercial lab. So they will tell us all of those all of those things that I just had in the last couple slides, from EC and pH and alkalinity to then the individual elements that are of interest to us. And then testing labs that are used to routinely running water analyses for agricultural water will tend to have ranges listed as well that you can look at. But one really great resource if you that goes into more depth than what your commercial testing lab is an online tool developed here in the US that's called WaterQual. And so you can go to cleanwater3.org. And what you can do is enter in all the results that you have from your own water test. You can also adjust the unit. So if your electrical conductivity was measured in a different unit, you can adjust that. If your alkalinity was measured in milliequivalents instead of parts per million, you can adjust that. So fill in the information that you have, and then hit submit. And then this is a really great resource where item by item, it's going to go through and tell you in more detail what are the potential issues with your water source. And so this particular one had high pH, but fairly low alkalinity. And so it says a pH level this high means some pH adjustment may be required in the spray tank for agrochemicals, because pH can affect solubility of pesticides or fungicides that we're using. However, in terms of root zone management, it's not really the pH that's important, but it's the alkalinity that's important. And so this alkalinity is a little bit on the low side. So it recommends using more nitrate-based fertilizers, for example, to make sure that my pH doesn't crash or go down too quickly. And then the tool continues on down the line with the other elements and attributes of interest. Then just to take a step back, I mentioned some different water sources that people may have, which are like shallow wells or deep wells, or drinking water from public water treatment facilities, or catchment ponds and surface water. And so on average, there's three types of issues that we think about with water quality. And I'm mainly going into chemical for the purposes of today's talk, which are like the salts and the pH and the alkalinity and so on. But we also do need to think about microbial water quality issues or physical water quality issues. So in terms of physical, we could think about those maybe from like catchment ponds, for example, where we often don't have great water clarity. There can be a lot of suspended solids in that water. And so we might have to add filters to remove those suspended solids before that water goes through our irrigation equipment, for example. And then similarly, some water sources, especially those like surface water and catchment ponds, and sometimes shallow wells, we have to think more about microbial water quality issues. And I won't get into details for today. Maybe that could be another great talk. But using these water sources, especially for food crops, but sometimes also thinking about plant health or root diseases for ornamental crops, we might have to install a disinfestation system to control that microbial load as well. And then if we're using municipal water, that's typically chlorinated so that it's safe for humans to drink. So we typically don't have microbial issues with that water. And as well, any sediments or suspended solids would have been filtered out by the municipality. So sometimes we do have to think about chlorine residue. This is mainly for hydroponic crops. So if your roots are immersed in a water bath, The chlorine residue can sometimes injure the roots, and I see more of an issue with that in the winter time when the cold temperatures of the water make the chlorine less reactive. So municipalities add more chlorine to their water, and then more of it stays in that active farm when it gets to your farm. But if you're growing in soils or potting mixes, the nice thing is the organic matter and the particles in the soil and potting mix dissipate those reactive chlorine species. So we're not worried about plant roots in that case. And then occasionally we're worried about fluoride if that's added for tooth health. A little bit more in terms of thinking through water quality. Often, especially with like salts, for example, or buildup of specific nutrients, um, the necessary water quality will also depend on the crop that's grown. Is the crop one that is tolerant of higher salts? Like tomatoes is more tolerant than arugula, for example. And then how closely the fertilizer used matches the crop needs. If there's not a very close match, then the added nutrients that aren't being taken up by the plant can sometimes build up to either toxic levels and injure the plant from high salts overall, or by causing nutrient imbalances, making it harder for other nutrients to get taken up. And then another consideration is whether the water is captured and reused or whether it is like a drip to drain system, which I would call an open irrigation system. And so in open irrigation systems, any excess water that is applied leaches to the floor or the ground or the soil. And if we're growing in container crops, a nice thing about these open irrigation systems is that's a way for us to control buildup of soluble salts in the root zone. So we can apply excess water, have our leaching fraction, and maybe it's bad for the environment because some water and nutrients leaches into the ground or the soil, but we can control the root zone salt levels. If we're in a closed system where excess water is captured and reused, I tend to see this in like hydroponic growers, for example. So here's a grower that has an NFT channel system for growing leafy greens. So they want to reuse their water. So sometimes you'll have to think about disinfestation to control pathogen spread. Usually we don't do that in NFT systems because we're moving a very large volume of water very quickly. So it's kind of impractical to do disinfestation. But we do have to think about nutrient imbalances and salts that can build up over time. So it helps to start with higher quality water that has less salts that can build up over time. And then as we add fresh water to that, it helps keep the system going. So also so I'm going to talk quite a bit about pH and maybe fixing issues with both high pH as well as low pH, as pH tends to be responsible for most of the nutrient deficiencies or toxicities that I see. And one thing to be aware of is that depending on how you're growing, that affects how quickly pH can change in the root zone of plants. And what I mean by that is if you're in a field soil, especially a really nice field soil with good cation exchange capacity, for example, we have very good buffering in the soil, and it will usually take at least a month, if not several months, for pH to change by more than a unit. And that's if you're taking fairly intensive action, such as liming to increase the pH, adding sulfur to decrease the pH, or fertilizing your crop. So soils are very well buffered and don't change that frequently. If I'm growing in true hydroponics, like deep water culture or raft pond hydroponics, pH can change by a unit in a day or less. And then if we're growing in, say, potting mixes, maybe with peat or coconut coir or so on, it can take about a week or so for pH to change by about 1 unit. So this could then also indicate how frequently it helps to test pH. So if I'm growing in potting mixes, my recommendation is to test pH of major crops in the root zone at least once a week and track that over time so you can take action And then if you're growing in true hydroponics, to track pH every day because it changes more frequently. And this was just an example. This was an experiment I did maybe 20 years ago or so, where I was growing hydroponic roses actually in directly in a nutrient solution, so kind of like deep water culture. And we had different percentages of nitrogen as ammonium. And roses had a preference for taking up ammonium first before nitrate. And ammonium, when plants take up ammonium, they acidify the root zone. And so what we're seeing here is we started at a pH of about 6. And in one day, pH went from about 6 to less than 4 in our highest ammonium treatment. So pH can change very rapidly. In the case of the lower amounts of ammonium, an interesting thing is pH changed by about a unit or so in a day. And then as that ammonium was consumed, the plants then had to take up the nitrate that was left behind. And then nitrate increases root zone pH as plants take up nitrate. So then my pHs were actually going back up with a fairly rapid swing after that. And then I want to contrast that with this was growing bedding plants, maybe petunias, I forget the exact crop, um, in a peat-based soilless potting mix. And so we had our base fertilizer that we were using at every watering, and then every week or so we were measuring pH. And our waters at Cornell have fairly moderate alkalinity, so pH was going up a little bit over time. And so what we had to do after about 30 days of growing is switch to an acidic fertilizer for a week, so a more ammonium-based fertilizer, and that kept pH in check. And then as our plants were growing older and it was getting later in the spring, pH was changing more rapidly. So another 20 days or so past that, we had to switch to an acidic fertilizer again to knock pH back down. So soil pH affects nutrient availability. And this is why we're interested in pH, I guess. So this is kind of our how pH affects nutrient availability in soil-based systems first, and then I'll show you a similar graph for soilless systems. And so for soil systems, it can be a little bit crop dependent, but we're typically targeting a soil pH of 6 to 6.5 as being optimum, because that gives us a good balance of availability for all of these nutrients. Versus if pH is getting too low, we have issues with calcium and magnesium availability in particular. Eventually, we could have issues with availability of nitrogen and phosphorus. And then if pH is too high, then we have issues with availability of these micronutrients like iron, manganese, boron, copper, and zinc. Um, so then similarly, for growing in soilless media, we have this chart. And soilless media tend to be not as well buffered as soils. We don't have the same cation exchange capacity. So we usually have a little bit narrower and a little bit lower pH guidelines. So kind of our general guideline is 5.5 to 6, with a few crops like geraniums and marigolds preferring pH a little bit on that high side of that, 6 to 6.5. And then we also have several crops like the petunia group or calibrachoa or Lysianthus in the cut flower world that prefer pH a little bit on the low side, the 5.5 to 6. And for those crops, they're not so great at taking up iron and manganese. And so keeping pH on the low side helps to ensure that they have enough iron and manganese. Versus for crops like geranium, they actually are really good at taking up iron and manganese. So we have to keep pH on that higher side, the 6 to 6.5, so that they don't take up toxic amounts of iron and manganese. So if we have high pH in our systems, this is what it can look like, which is micronutrient deficiency. So iron and manganese are a couple of the micronutrients that are needed in the greatest quantities. And so if we don't have enough of them, The symptoms show up on the top parts of the plant. So that's always important when a grower tells me about yellowing of leaves that they have. I'm always like, okay, is it the top of the plant, the bottom of the plant? Meaning, is it the young leaves or the old leaves? And so for iron and manganese, it's the upper or young leaves that are affected. And for iron, it's really yellowing between the veins that is symptomatic of iron. As well as manganese is like that too. Usually the symptoms aren't quite as uniform with manganese. And peppers are a vegetable plant that's really sensitive to iron and manganese deficiency. Tomatoes are quite a bit less sensitive, so maybe whoever took this photo had to work really hard to get this iron deficient tomato. And then in the ornamental plant world, petunias and calibrachoas and pansies are crops that are also really sensitive to high pH, which can cause iron and manganese deficiency. So if you're growing in a soil-based system, causes of high soil pH can come from either soil that's naturally high in pH, so just inherently it can come from excessive addition of compost. So most of the compost that we use are a little bit alkaline, meaning the pH is a little bit more than 7. And so when we incorporate it into our soil, it can raise the pH. It could also indicate if we have high pH, that could mean excessive liming of soil. We added too much lime and raised the pH too much. It could also mean that the fertilizers we're using are nitrate based. So as roots take up nitrate, they tend to increase the pH of the root zone. Or as we were talking about alkalinity, it could be due to high alkalinity of the irrigation water. So kind of the liquid limestone that we're adding. So correcting high pH, I'll talk first about soil systems, and then we'll talk a little bit more about soilless systems. So in terms of soil pH, we have conventional approaches and then organic approaches. So we can add elemental sulfur into the soil. I'll have a little bit more detail on that. That can be a multi-month process. So you want to test your soil pH a few months before you want to do it, maybe or use it, maybe even the fall before you want to use it. You can also add aluminum sulfate or iron sulfate. In terms of the fertilizers you choose for adding nitrogen to your plant, then you can use more ammonium-based fertilizers, and those will also decrease the soil pH over time. And then if you are irrigating your crops and you have an injector, you could also inject acid, such as sulfuric, phosphoric, or nitric, and that will neutralize the alkalinity of your water source, so that at least then you're not further contributing to soil pH increasing over time. In organic systems, we can use elemental sulfur. It needs to be products that are registered for organic use. Peat is inherently low in its pH, so as long as it hasn't been limed, we can use peat incorporation, or pine bark mulch is also low in pH. This tends to work well maybe for like garden kind of purposes, but often the volumes that are required probably make it not so compatible with farmers or growers. And then if we want to neutralize our water's alkalinity and we're an organic grower, we can use citric acid or acetic acid if they're labeled for organic use. So in terms of elemental sulfur, sorry, Americans use pounds and square feet and so on. I'm sure we can work with you to get you the conversion factors here. So these are rough guidelines for how much elemental sulfur to use based on our present soil pH. So if our soil pH is 7, for example, and we want it to be 6, we would use 2 pounds of elemental sulfur per 100 square feet. And then some guidance here for sandy soils, we reduce these amounts by 1/3. So they have less buffering overall, so it's easier to change pH. And for clay soils, we need to increase that amount. And then if our guidance called for adding more than 4 pounds per 100 square feet, That's a lot to add at one time. So then we want to do split applications that are 6 months apart. Um, and and then the effective sulfur requires active microbial community. So warm, moist, aerated soils and not waterlogged soils will give us the best effect. And it can take up to 12 months to have the full pH effect. So maybe what this means is that fall, when our soils are still warm, is a really good time to test our soil pH. And if we do need to add elemental sulfur, we can take advantage of that warm soil and add that now before we have a crop that is actively going to be growing in that soil in the spring. So a little bit more about alkalinity, and this will also transition into how to decrease the pH for soilless growers. So alkalinity, as I said, is the ability of water to neutralize acids, the carbonates and bicarbonates that are in our water supply. And I always like to refer to it as liquid limestone because it's like, oh yeah, alkalinity raises pH just like limestone raises pH. So if your water source is high in alkalinity, kind of the options that we have, we could either change or blend the water source. So some maybe medium-sized growers I know or larger greenhouse growers will actually collect their rainwater. And rainwater is very high in quality. It's low in salts and other impurities, and so also has an alkalinity of essentially zero. So that could be blended in with your existing water source to decrease the alkalinity. That could also be a good thing to do if you had high overall salts, for example. Then you can switch to a more acidic fertilizer, and I'll show you examples of that in a second. So fertilizers that have a higher fraction of ammonium and less nitrate. And then similarly to soil growers, we can also inject acid into the irrigation water to neutralize the alkalinity. And what that acidification does, so here's an injector. Um, I think it's pulling up fertilizer, but we'll pretend it's pulling up acid. And so the acid gives us H plus, or this proton source, and that reacts with the carbonates. And that gives us carbon dioxide, which just bubbles out of our water, as well as oxygen. So that effectively neutralized the alkalinity in the water. And how much to use, I'll talk about in a second. There's some online calculators that you can use. So for conventional production, we can use a wide range of options from citric acid, which is a weaker acid, to nitric, phosphoric, and sulfuric. And for these last three, we could also think about the fertilizer effect that they give us. So they do provide some nitrogen, phosphorus, or sulfur, respectively. And then for organic growers, you would need to check what qualifies for your organic program, but there are usually some citric and acidic acids that qualify. They are weaker acids, so more is required to have the same neutralizing effect as, say, sulfuric acid, which means ultimately it's going to be more expensive than if you're a conventional grower. Whenever you're using acids, we always have to think about safety first. So this means wearing safety glasses, wearing gloves, wearing a full sleeve shirt. I've worked with acids before and later in the day found holes in my shirt, which meant that acid dripped onto the shirt. And I was very happy I was wearing that shirt because at least the shirt took the caustic acid instead of my skin. So those are important things. And we always have to prepare them in well-ventilated areas too, because their fumes can be harmful to us as well. Then, if you remember your high school chemistry, we always add acid to water, not the other way around. So we don't pour acid in a container and then add water on top because it can bubble over and injure us. Um, and overall, nitric acid is caustic and has these harmful fumes. So it is commonly used, but we do have to be really careful about using it in well-ventilated areas. And sulfuric, phosphoric, and citric, citric's safer because it's a weaker acid, but we also have to be careful and use proper personal protective equipment. Usually sulfuric acid tends to be cheapest, and then the others are more expensive. And we talked about the nutrients that we can get from the acid. Um, and so sometimes phosphoric acid is maybe not the best choice because we might already have high phosphorus in our soils, or our fertilizer might already have the phosphorus we need for like our greenhouse container crops. So if we're adding phosphoric acid, we could be adding too much phosphorus. And then we can think about the implications that has for groundwater or surface waters with like phosphorus causing algae blooms, for example. So how much acid to use? This depends on your water's alkalinity. And essentially, we need to add enough acid to bring the pH down to about 5.8. This neutralizes most of the alkalinity, but not all of it. So it gives us it usually results in an alkalinity of about 80 parts per million calcium carbonate. So that puts us in kind of the good level, not too low for alkalinity and not too high for alkalinity. So you could do this through the trial and error method where you add small amounts of acid to a concentrated stock tank, run that water through the injector and test the hose end and find the right amount of acid for your water where ultimately the hose end is coming off at a pH of 5.8. Or you can use an online calculator, which I'll show you in a second, where if we know our water's alkalinity, we can calculate exactly how much to use to neutralize that based on the different acids that we have available. And then the one thing that online tool does not have is citric acid or acidic acid calculations. So if you're an organic grower and you're wanting to use citric acid, here are some calculations that I found online. So for every 50 parts per million of alkalinity you want to neutralize, we would use 1 ounce per 100 gallons of a granular citric acid. Um, or if we're using liquid, that's usually a 50% citric acid product. We'd use 1.5 fluid ounces per 100 gallons. So that means if we're running our water through a fertilizer injector, that's a 1 to 100 injector, for every 1 gallon in the stock tank, we would use 1 ounce of this water, or I guess 1.5 fluid ounces of this water. So for those other types of acids, we can use an online calculator that's called ElkCalc. And you put in the pH of your water, the alkalinity of your water, and your target alkalinity. I always recommend target alkalinity, again, be about 80 parts per million because we still get some buffering from it. And then we choose which acid we're using, and then we hit submit. And then the calculator tool tells us the amount to use. So if we're using a 1 to 100 injector, per gallon of concentrate stock tank, we would need 1.1 fluid ounces or 33 milliliters per gallon. If you're growing container crops and soilless media, maybe you're growing that petunia crop, for example, and we need to keep pH down into 5.5 to 6. Maybe you test your pH and your pH is like 6.5. That would make me worry about getting iron deficiency. That will happen pretty quickly. So there's also quick methods to decrease pH, and that would be doing a one-time drench with either phosphoric or sulfuric acid. And sometimes I visited operations where they don't have, say, sulfuric acid on hand. They're concentrated, they're 96% sulfuric acid, but they have a auto parts store down the road. Battery acid is 35% sulfuric acid, so it's just not as pure as the 96% sulfuric acid. So we just need to use more of it. So in this case, a one-time drench with 5 ounces of sulfuric acid per 100 gallons of water. And again, that means if we're using injector, that's a 1 to 100 injector. So that would be for 1 gallon of stock tank, it would be 5 ounces. And then at the hose end, we're getting the 100 gallons of water that has been treated. Another tool that we have for soilless growers of container plants is that we can also match our fertilizer to the water's alkalinity. And we can kind of use this for soil growing too. I just don't have exact metrics of what we should be using. But for soilless growers, if our alkalinity is low, we're going to use a fertilizer that's more basic. It has less than 10% ammonium-based nitrogen, and then 90% or higher nitrate-based nitrogen. And then if my alkalinity is higher, like 150 to 250 parts per million calcium carbonate, then I would use a fertilizer that has 40% of its nitrogen is in the ammonium form and 60% is in the form of nitrate. And so similarly, the different fertilizers that we use have a potential acidity or basicity on them, where the more nitrate ones are basic, and they actually, if we're thinking about field growing, they add to the liming potential. So that would mean 1 ton of, say, potassium nitrate is like the equivalent of adding 520 pounds of limestone to a field. And then on the other end, if we have an acidic fertilizer, like ammonium sulfate is 100% ammonium, adding a ton of ammonium sulfate will take a ton or 2,200 pounds of limestone to neutralize that acidity. So I talked quite a bit about high pH and how to solve high pH problems. Alternatively, you might have issues with low pH. And for low pH, we typically see 3 types of symptoms that can show up on plants. I'll show examples from ornamental plants that I'm more used to working with. So we can get lower leaves showing iron and manganese toxicity, and so they might show us bronzing or chlorotic and necrotic spots on the lower leaves. Some plants show us black or purple speckles on their lower leaves, and that's their symptom of iron and manganese toxicity. And then some plants just have reduced plant size overall, but not specific symptoms on the leaves. So zonal geraniums are an example of a crop that is sensitive to low pH, and they get iron and manganese toxicity. And so this bronzing or this yellowing and then necrosis on the lower leaves in fairly regular patterns is what develops over time as the pH goes down, and the plants take up too much iron and manganese. Begonias are an example that instead of showing that kind of bronzing, the yellowing, and then necrosis, they show more of these black or purple speckles on the lower leaves. And these photos come from Brian Whipker at North Carolina State University. He has a lot of great resources at this website, eGrow, which is e-grow.org, with lots of really great fact sheets on different crops and their fertilizer requirements and pH requirements. This was an example of petunias. Usually we think of petunias as liking a low pH so that they can take up a goodly amount of iron, but also if pH gets too low, so in this study he had a pH down to 3, it didn't really show leaf symptoms, but what it showed was a much smaller plant than its counterparts that were at a pH of 5.1. And poinsettias are another crop where they don't show us specific leaf symptoms of low pH, but we see overall smaller growth. And interesting, I guess, not good pigmentation of the bracts, which is what we want to be colorful as it progresses closer to the sales season. Okay, so if we need to raise pH, some things to take into account are if you are adding acid, stop adding acid because it's not helpful at this point. Also make sure that you're using nitrate-based fertilizers. And then if you're in the soil world, you would do a limestone addition. And I was trying to put together a few slides on how much limestone to use. And it's complex because it depends on your soil type, the depth that you want to incorporate limestone into your soil, and then the source of limestone that you're using. So maybe my one bullet point response is to work with a soil testing lab to get their recommended limestone incorporation rate, or work with your friends at Perennia to get some guidance there as well. And then if you're a soilless grower, there are methods where you can add flowable lime or potassium bicarbonate. So those are bases, and you can apply those products through the fertilizer injector to raise the pH in a fairly quick fashion. I won't go through this in much detail, but if you do go that route where you need to add flowable lime for fast pH increase, a couple things to be aware of is that the particles can be abrasive. So if you're running that through the fertilizer injector, you would then want to flush out the injector and any other equipment after that application with clear water so that those abrasive particles aren't left behind. Don't apply through drippers. So drip emitters can get clogged from that residue. So this would be, I guess, overhead watering. Um, and then if the foliage gets wet with this flowable lime, it can cause phytotoxicity. So then we'd have to go back and mist the foliage after applying our flowable lime. So that's all sounds like a lot of work to me. So maybe the recommendation is to monitor your root zone pH and be proactive about adjusting it using the fertilizer approach before we get to the point where we have to add flowable lime to rapidly increase the pH. And so similarly, there are recommendations for how much potassium bicarbonate to use. And we also want to mist the foliage after applying if our leaves got the product on it so that they don't have phytotoxicity. If we have overall high salts in our irrigation water, there's some options that we have. So if we're growing in soilless substrates, as I talked about before, we can do leaching of those container grown crops to push out the high salts. Um, in high tunnels, and then if we're outdoors in a field, not under cover, we rely on Mother Nature and the rain and snow that we get to help flush those salts out of our soil. Ideally, our soil will have good drainage so that that salt goes somewhere. But if you're in a covered high tunnel, or I guess a covered greenhouse and growing in the soil, we don't have that kind of leaching tool. So your options are a lot more limited at this point. So you might take away that high tunnel cover, that high tunnel plastic for a winter, for example, if you don't have a crop growing, and let Mother Nature kind of act on that soil. Um, I guess then being careful with not over fertilizing and over composting is important so that we don't have that salt buildup as much to begin with. And then I have colleagues such as Judd Reed from Cornell Cooperative Extension, who's doing research on cover cropping in high tunnels as another way to mitigate high salts. And then other options could be, again, looking at changing water sources. So if your well is high in salts, could we switch to a rainwater? Or pond water, and we'd have to think about other water quality characteristics of pond water or surface water. But changing water source could be an option that could be a pretty expensive option, or treating the water with reverse osmosis to filter out the salts could be an option. But those systems are quite expensive upfront, as well as the ongoing costs of replacing the filters that filter the water. Okay, that was all I wanted to get through, I guess. That was my rapid fire water quality discussion. So, yeah.
No, that was awesome. Super thorough. I like how you touched on soil systems and hydroponic systems, but also like the closed and recirculating. I thought that was really cool. Um, so I guess you kind of touched on the recirculating systems and, having to be aware of the acid that you're using and the kind of residual fertility that's sort of in that acid.
Mhm.
Um, so for example, like how often, I guess, would you recommend either swapping out your water in a system like that or sort of mixing with fresh? Like, is there sort of a
Yeah, so maybe the a classic system I think about for that system are like NFT growers, so growing like hydroponic lettuce in those NFT channels. Their water reservoirs are fairly small, and so salts can build up pretty quickly. Maybe, and often we're adjusting fertilizer concentration based on EC. So like our EC is stable, but maybe
Yeah.
nitrogen and potassium are going down because sodium and chloride are going up. So our EC stays the same. So the typical recommendation, and it could take time to get used to each system, but maybe every crop cycle is when you think about draining that reservoir, making sure you're doing that in a safe, responsible way, whatever your location allows, and then rebuilding that with fresh water at that point. Um,
Okay.
the alternative would be sending a sample to a lab for analysis, and then being like, okay, what are the individual elements? But what I find is, at least for kind of smaller growers, it's almost more expensive to send a sample to a lab than to drain that reservoir, and rebuild with new fertilizer.
Yeah, no, and I appreciate you mentioning that because I have seen the system where it automatically injects like an acid to maintain the pH and the EC, but we're not looking at the content and the nutritional breakdown of that water.
Exactly.
And
Yeah. Yeah.
that's a scary pitfall, or it can be.
Yeah. It's like we have a little bit of data, but not all the data that we
Yeah,
need. Yeah. Hmm.
absolutely. And then just one sort of final question. So for those who are kind of deciding to maybe follow their water more closely and pay more attention to the water they're supplementing, it sounds like obviously submitting a water test is a good place to start, but also potentially investing in like a pH EC meter just to sort of, you know, pay attention to maybe the concentration and the quality of the water we're injecting to the crop. Is there anything else maybe you would recommend
Yeah, those are
there?
great. Getting handheld pHEC meters, they might cost you $200 or $300 or so. They're they're really workhorses because you can monitor the water source itself. You can also monitor the water after it goes through your injector system, so you can check if you're adding the right amount of fertilizer, are you hitting the EC target that you're supposed to, and then you can monitor the root zone itself. Like you can either test the field soil or take substrate samples and test them for pH and EC. So
And just to, so you said, sorry, you can check sort of your soil or substrate ECPH by using these sort of handheld meters. And would that just be like kind of create a slurry?
yes,
Um,
right. I love that you asked that question because usually we can't stick them directly into the soil. So what we have to do is get an extract from that. I like to use the 1 to 2 dilution method. So we take 1 part soil by volume and then 2 parts distilled water or reverse osmosis water, and mix that together to get kind of a slurry. And then if you carefully do it with your meters, you can put them directly into that slurry and measure it. If you like being tidier, you can pour that slurry through a coffee filter, and then test the liquid that comes out of the coffee filter.
awesome. Yeah. So some really like accessible on-farm quick checks that we can kind of combine with the information that we know about, you know, what we're adding in through fertilizer, and then also maybe that original sort of water test that we played
Yeah,
around with.
exactly. Yeah.
Cool. All right. Well, thank you so much, Neil. That was awesome. And I
All
hope we see you
right.
soon.
Thank you. Have a good fall. Get all your chores done before winter, everyone.
Wise words.
Right. Take care, myself included. Oh boy.
Yes.
Take care.